Mary Wootters, the presenter. Hi, Mary. And so, Mary, if you can put your slides up, if you can share your screen.
Sure. Wait just a
okay.
second.
Okay.
Can you see this?
Yes. Maybe make it full screen, kind of thing.
Is it not?
No. It's yeah, it's pretty small for at the moment.
Oh, what can you see? Can you just see the window, or can you see other stuff too?
I can see other stuff too, not just the slides.
Oh,
it's yeah.
Cover up my Slack there.
Well, it's
interesting. Okay, sounds good. Okay.
This is readable, but it wouldn't hurt to make it bigger if you can.
Let me try this again.
I think it's like an extended desktop.
Yeah, I have a huge monitor, and I'm trying to share just a window.
Okay, well that's your mistake, then, is having
too much
having such a large. Yeah.
So hang on.
Can you make our monitors large too?
Maybe that's the solution.
Let's see.
Give me better eyesight. That would be the.
Oh, I see.
You need to download the bigger monitor.
I see. So you're just seeing my slides, but within a bigger monitor.
Yeah, it's okay. It's not worth spending a lot of time on.
Okay, sorry about that. Let me get rid of all the other stuff then. Okay, sorry. Well, this is what it is.
It is what it is. Okay.
Okay.
So our speaker, as you can see, is Mary Wootters, who will talk about something that sounds like pretty basic high school mathematics, but I think it's going to end up being pretty sophisticated stuff. So Mary, please.
Cool. Yeah, well, thanks. Thanks everyone for tuning in. Thanks, Ken, for the introduction. Sorry about the technical difficulties, and I hope that the slides are big enough that you can see part of them. You can see most of them at least. Hi, my name is Mary Wootters. I'm an assistant professor of computer science and electrical engineering at Stanford. Like Ken said, today I'm going to talk about some fun facts about polynomials. Cool. Okay, so what is this talk about? So as you might have guessed from the title, the talk is about polynomials. So by this, I don't mean anything fancy, just like normal polynomials like this one that like Ken said, you might have regarded as high school math that you've sort of been working with since high school. You might be thinking, like these are pretty basic objects, right? Like, don't we already know everything there is to know about polynomials? What more is there to say? But it turns out that yes, while these are very basic objects, we're still learning things about polynomials. And that's sort of what this talk is about, is what are some of these new things that we're learning about polynomials. So what I'm going to do today in this talk is I'm going to tell you 4 fun facts about polynomials. So 2 of these facts are going to be sort of classical facts. These are facts you probably already know. And 2 of them are going to be newer facts. These are facts that maybe you don't know, and perhaps that you might even find counterintuitive. At least I found these facts counterintuitive when I first encountered them. I think these facts are interesting on their own. After all, they are fun facts, that's the point, but they're also useful. So actually the classical facts that I'm going to talk about are sort of classically useful in the sense that they are behind sort of classical encoding schemes known as Reed-Solomon and Reed-Muller encoding, which are used all over the place whenever you want to protect data from noise. So in particular, in applications in communication and storage. So part of what I'm going to do in this talk is also talk about some of those applications. And the newer facts that I'm going to talk about are inspired by those applications. So I'll sort of present them side by side. So that's the plan for the talk: 4 fun facts and some applications. I should say this is going to be like a super high level talk. I'm not going to go into any like deep mathematical detail. So I'll tell you the facts and I'll try to like wave my hands about why they might be useful, and maybe wave my hands a very little bit about some intuition for why they might be true. But I'm not going to go into too much detail. So my hope is for this just to be kind of a fun high level talk in what I know is a long day of talks. So that's the plan. And I hope also that it will be accessible to and anyone who's here, so you don't need any fancy algebra to follow. Okay, so let's get started. Actually, before I start talking about the polynomials or anything like that, I want to introduce a running example that I'm going to use to kind of motivate things as we go along. And so this example is distributed storage. So I'm going to present a very, very stylized version of distributed storage. Can you all see my laser pointer here? Yes? No?
Yes, yes.
Yes, good. Okay, cool. Yeah, so I'm going to present a super stylized version of distributed storage here just to make, it's a theory talk, just to make things easier. So suppose that we have some file F, and it's just a bunch of bits. So here's F, and I'm going to break F up into a bunch of blocks. I'll call the first block F0, the second block F1, ... all the way up to the third block, which is, the kth block, which is Fk minus 1. Right. And for convenience today in this talk, let's just assume that each of these blocks are bytes, so just 8-bit long strings. Like in actual practice for distributed storage, like the blocks would be much, much bigger, and then you'd further subdivide them into bytes, and you'd sort of work with bytes across blocks and whatever. But let's ignore that layer of complexity and just say, okay, I have some file, it's just a bunch of bytes. Okay, and so these bytes, these are just bit strings, strings of length 8. So if you like, it might be convenient for this talk to think of them as a number between 0 and 255. Actually, what would really be more convenient for this talk is if you were to think of them as an element of F256, which is the finite field of size 256. So finite fields are, if you don't know what that is, that's fine. It's not a prerequisite for this talk, but I actually just want to do a quick aside about what I mean by that, because I'm just going to be using that notation F256 a bunch. So what is a finite field? A finite field is just a finite set of things that you can do arithmetic on like you're used to. So what do I mean by F256? So this is just the finite field with 256 elements, and you can think of each element of this finite field as being a bit string of length 8, which is convenient because that's what we said that we wanted our blocks to be. Okay, so each element is a bit string of length 8, like this one. And it turns out that you can actually do arithmetic on bit strings of length 8 in a kind of sensible way. Addition is just going to be bitwise XOR, so just XOR each of the bits together. So it's pretty straightforward. And it turns out that there is actually a way to multiply bit strings together that makes sense. So I can take 2 bit strings and I multiply them together and I get some other bit string. And it turns out you can define this multiplication in a way that plays nice with the addition and obeys all of the normal axioms of arithmetic that you're used to from the real numbers. What this multiplication isn't too important. It's not bitwise multiplication. It's not multiplication mod 255. It's something more complicated, but it turns out to exist. Okay, sorry, so getting back to this example and aside, the point is that whether or not you're thinking of these blocks F as numbers between 0 and 255, or if you're thinking of them as elements in our finite field, one thing that's going to be useful in a moment is that we can add them together and we can also multiply them by each other in a sensible way. Okay, so back to our distributed storage example. We've got this file F. We've broken it into a bunch of blocks, which we can add together and multiply together and do arithmetic on. And now we want to store these blocks in some sort of, let's say, a distributed system. So I have a bunch of different storage nodes, and I'm going to put one of my blocks on each different storage node. So 1 block per storage node. Great. There's a problem with this approach, which is that if, for example, one of the storage nodes disappears, either it's temporarily unavailable or, as the graphic indicates, it just in a puff of smoke, we've lost data. That block F2, I didn't back it up anywhere. That was foolish of me, and now it's gone. Okay, so instead of doing that, what we'd like to do is something called distributed storage with erasure coding. So basically, we want to introduce some redundancy before we store our data so that we don't lose it if anything bad happens. So we have our data blocks here, F0 through Fk minus 1. And what we're going to do is encode them somehow. I'll say a little bit more about how in a moment, into sort of encoded blocks, n encoded blocks, C0 up through Cn minus 1, so that basically n is going to be bigger than k, and I'm trying to introduce some redundancy here. So just as a first pass, you might think about maybe I'll just duplicate each of these blocks 2 or 3 times or something and call that my encoding. And then I'm going to take these encoded blocks and put those things on my storage nodes. And the hope is that, if you've introduced redundancy in an appropriate way, that if one of these storage nodes then goes poof in a puff of smoke, you haven't lost information. You should still be able to recover the original file from everything that you've stored. So that's the basic setup for erasure coding. Okay, so now that I've talked about my setup, let's get into the polynomials. Yay. All right, fun facts 1 and 2. So to introduce polynomials into the picture, let me tell you how to use polynomials to encode data. So you might have seen this before. This is something called Reed-Solomon encoding. It's a very classical idea. So we have our file f, which is just a bunch of blocks. And remember, I can multiply these blocks by each other. I can add them to each other and stuff like that. I can do arithmetic with them. So it makes sense to define a polynomial with these blocks as the coefficients. So my polynomial is going to be f of x equals f naught plus f1x plus f2x squared plus dot 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 plus fk minus 1 x to the k minus 1. And so my coefficients here are just the data blocks. Okay, great. Now that I've done this, what I'm going to do to encode my data is just evaluate this polynomial at n different evaluation points. So I'm going to evaluate this polynomial at a0, at a1, all the way up to an minus 1 for just whatever my favorite points are, a0 or an minus 1. And I'm going to call this my encoded data. Right? So if n is bigger than k, then hopefully I've introduced some redundancy here. So if you haven't seen this before, this might seem like kind of a strange thing to do, but in fact, it's a very good thing to do, and it's actually done a lot in practice. So this is a good way to encode data. So let me tell you why just by looking at a quick example. So for example, with k equals 3 and let's say n equals 4. So for k equals 3, I only have 3 data blocks, f0, f1, and f2. So those are going to be the coefficients of some quadratic polynomial f. So here's my quadratic polynomial f, some parabola or something. So n equals 4, that means I have 4 encoded blocks. So maybe I'll take 4 different points, my 4 favorite points, and I'll evaluate them at this polynomial. And that's going to give me 4 points on this parabola. And I take each of those points, and let's say I ship them off to a separate storage node in this sort of running example of distributed storage. Okay, so I claim this is a good thing to do. In particular, I claim that it will help us in this situation where one of the storage nodes, or equivalently one of the evaluation points, just sort of goes poof and goes up in smoke and disappears. Our goal is that if this happens, we don't want to lose data. Okay, so why is this a good idea? Okay, so actually, right before this talk, I just came from teaching a class at Stanford, so I'm still a little bit in teaching mode, so y'all are going to get a quiz. I know you didn't sign up for a quiz, but you're going to get one anyway. Okay, so here's the quiz. So suppose, hopefully it's not too hard a quiz, it's also just to have some sort of interaction in this awkward online format. So given 3 points, these points, fa1, fa2, and f of a3, think about how can you recover f of a0? And then I'm also interested in how much information does it actually take to recover f of a0, right? So if you think about contacting these different storage nodes and downloading information, how much information do you need to download from these to recover f of a0? So if you all go now to polev.com/cs265, CS265 is just the name of the class I'm currently teaching, and so therefore it is the name of my Poll Everywhere account at the moment. But if you go here, you should be able to see a poll where you can tell me how many bits do you think it takes, how much information. So do that now, please. So I think when I first started, there was something like 77 people watching plus 20 panelists, and so far there are 13 respondents. So I bet we can do better than this. Even if you think it's not a hard question, please just humor me. Cool. Can I share this screen?
We're busy accepting cookies.
Can you guys see? So if you can see my whole screen, can you see the answers to the poll here or no?
No, sorry, I can't see them.
All right.
No, I think you're just sharing that specific app.
Okay. So let me. Oh, that's good. That meant that you couldn't see my email before. That's great.
So this is anonymous, by the way, right?
Yeah. Fully anonymous.
Okay.
No judgment.
Okay, good. Okay.
Share application. Aha. All right. Can you see it now?
Yes.
Yes.
Technology. Cool. Okay. So there's it seems like we've got some responses. So lots of people think 24 bits, some people think 8, some people think 16, some people say it can't be done. Cool. Okay, so let's, can I stop sharing that one and continue sharing just my slides? Share. Okay, make that one go away. I think I figured out the interface. This is cool. Cool. Okay, so thanks folks for participating and humoring me. Okay, so what are the answers to this quiz now that I know that at least 28 people are engaged? Okay, so the answer is actually you can do it, and like the majority said, you can do it with 24 bits. Right, there are 8 bits per thing, so this is basically downloading all of the information. And how do you do it? You do it with polynomial interpolation. Right, so here's the point I wanted to recover, and I know that I have these 3 points. Well, 3 points determine any parabola, right? There's only one parabola that goes through any 3 points, just like there's only one line that goes through any 2 points in general. So if you have these 3 points, you can do normal high school polynomial interpolation and recover this parabola. And once you've recovered this parabola, then you can evaluate it at f and get this missing point. Right. Okay, and how much information does that take? That takes 24 bits of information, 8 bits from each of these 3 points. Okay, cool. Let me deactivate that poll. All right, so far so good. So what we've just discovered, or probably what you already knew, is fun fact 1 about polynomials. Right? K evaluation points are enough to recover a degree k minus 1 polynomial. In particular, 3 evaluation points are enough to cover a quadratic. Yay. Okay, so you probably already knew this fact, seems pretty basic, but it turns out just to be mind-bogglingly useful. So I already just sort of sketched this application in distributed storage. In fact, this is used in some distributed storage schemes to protect data from erasures. It's also useful in communication, sort of in a similar way, and it has sort of a whole host of other applications. Just one quick example that might surprise you, like a QR code here. This is a polynomial that's written in binary and arranged in a grid. So it really shows up all over the place. And the buzzword for this thing is Reed-Solomon codes. So to say this fun fact, k evaluation points are enough to recover a degree k minus 1 polynomial in some jargon, it's just to say that Reed-Solomon codes have good distance, basically. Cool. Okay, so that's fun fact 1. Maybe you already knew it. If you didn't, now you do. And in either case, it's mind-bogglingly useful. Super cool. All right, but let's return to this quiz because the point of this talk isn't fun fact 1, it's maybe some newer fun facts. So returning to this quiz, you might think, sort of looking at this, that perhaps this strategy was a little bit wasteful, right? We just downloaded 24 bits in order to recover only 8 bits. So some people said 8 was all you needed in the quiz because that's really all you want to recover. Perhaps that's why you clicked that. All right, so this seems wasteful. Like, do we need to download 24 bits in order to recover only 8? Okay, so next quiz question, refresh your poll everywhere page now. The question is, can we do better? And in particular, one way you might think about doing better is like, what happens if we just ignore one of these evaluation points? Like, I don't want to look at it. Can I do better in terms of the amount of information I download by just looking at these 2 evaluation points, right? So there's only 16 bits in these 2 evaluation points. Like, can I do it with these 16 bits? Okay, so go to the poll everywhere thing, click your answer, tell me what you think. And now that I know how to use this interface, let me share that screen. Hopefully everyone can see this now, top of my slides. Cool. So lots of people, so far the majority say you can recover some information about it, but not pin it down exactly. Some very few people say you can recover it exactly. Some people say you can't learn anything about it. Okay, so I guess let's reveal what the answer is. Actually, the majority is incorrect in this situation. So majority of people say, or 50% of people say that you can recover some information about it, but not pin it down exactly. Hang on, let me stop sharing this poll. There you go. But it turns out that actually you can't learn any information about it whatsoever. So you can't learn anything. And why is that? Okay, well, we have these 2 points, and we want to know what is this third point. Well, given these 2 points, actually this third point could really be anything, because all we know about it is that it's the third point on some quadratic that goes through these 3 points. But like if it were up here, there'd be some quadratic that goes through those 3 points. If it were down here, there'd also be some quadratic that goes through those 3 points. Right? It could really be anything. There'd be some quadratic that goes through those 3 points. So not only do we not learn f of a naught in this situation, we actually don't learn anything about f of a naught. Okay, this was not the new fun fact. This is also a classical fun fact. Actually, right now it seems sort of like a bug, but it's a feature in applications like secret sharing. It turns out to be good that you can't recover any information about f of a naught in this situation. But it's a bit of a downer for us. Okay, so if we want to do better, we're not going to do better by looking at fewer points. So the question is still, can we do better? You all just said that no, we can't really do better by looking at fewer points. But it turns out, and this is the new fun fact, in fact, you can do better. And you can do better by looking at more points, kind of counterintuitively. So if you look at more points, but download fewer bits from each, it turns out you can actually do better. So do better than 24 bits at least. So for this particular example, I can do it with 20 bits, although the amount that I can do better by gets bigger as the examples get bigger. Yes, the basic idea is, so each one of these evaluation points, these are 8 bits, but we don't need to download all 8 bits at once. I could download like half of an evaluation point. And it turns out that by looking at more of these evaluation points and downloading like only a fraction of each of them, you can actually do better. So this is fun fact 2. So this is a new fact, sort of originally observed by Shanmugam et al. In 2013, and then also has been worked on by myself and Venkat Guruswamy and others since then. This is called low bandwidth polynomial interpolation. So suppose that f of x is a degree k-1 polynomial over f256. This is this funny finite field thing. Then it turns out you can recover any evaluation point f of a using fewer than 8k bits. Here 8k would be the naive thing where I just contact k different points to interpolate the entire polynomial and download 8 bits from each of the points. So I can do better than that. I can download fewer than 8k bits from the remaining evaluation points. And once again, the idea is I'm going to query more points, but download less information from each. Okay, so you might be wondering how many fewer bits can you query? Let me just give you one quick quantitative example just in this particular setting for how that 20 bits instead of 24 looks. So for this particular setting, like I have these 3 data blocks. I'm going to encode them actually as quite a few encoded blocks, as 11 encoded blocks. And then the idea is that if one of these encoded blocks disappears, so naively, if I wanted to recover the missing data, in this case, it would be f of a2, I would contact 3 different storage nodes and download 8 bits from each. So 3 bytes, it's 24 bits. But it turns out that by contacting all 10 surviving nodes, in this case, it's possible to just download 2 bits from each of them and still recover the missing data. And 2 times 10 is 20, which is less than 24. So at least that's at least a little bit of a win. Yeah, and the basic idea here, I'm not going to go into detail about how you do this, but the basic idea is there's something like really nice about how these polynomials are encoding data. So the data is like really sort of spread out over all of the points. So you can kind of recover any one point by sort of looking around. And schemes which can do this, not just Reed-Solomon codes, but more general coding schemes which can do this are called regenerating codes. So I'd point you to this survey by Demakis et al. For a nice overview. Okay, so how many bits can you actually get away with for this fun fact 2? Well, it depends on the parameter regime. In this sort of very small example that I just showed you, you encode 3 bytes into 11 bytes. The straightforward scheme has 24 bits. The improved scheme has 20 bits. And your improvement factor is not too much, 1.2x. But as k gets bigger, you can do better and better and better. So for example, if you have 128 bytes and want to encode that into 256, you can end up getting an improvement factor of about 4x. And more generally, if you have k bytes and you want to encode them into like k times 1 plus epsilon bytes, so just a little bit of improvement, or sorry, just a little bit of overhead, your factor of improvement is going to scale like log k. So the bigger k is, the better you can get away with in terms of how much you can download. Yeah, so these schemes which do this are joint work with myself and Venkat Guruswamy. Cool. So there are a lot more fun facts of this flavor. I'm not going to go into detail about them, but yeah, basically I just told you sort of a very simple version of this where I was like just looking at over F256 and there was just one failure, but it works over lots of different parameter regimes, in particular over lots of different finite fields. So if you're interested in different finite fields, as long as they have reasonably small characteristic, works great. It works with multiple erasures. So if multiple data points or multiple evaluation points just sort of poof and go missing, you can still get a scheme that works pretty well. It works for variations on Reed-Solomon codes, like algebraic geometry codes. And it actually, interestingly, does not work in kind of a provable sense over prime fields. So just to say some jargon, if you're working over a prime order field, it turns out that you cannot do this provably. This Ben Hamuda et al. Paper shows that, and this turns out to be good news for secret sharing, for leakage resilient secret sharing. So, all right, so yeah, there are tons of fun facts of this flavor. So I'm not going to go into any more detail about these fun facts, but just to sort of recap what we saw so far, fun facts 1 and 2. So for a polynomial f of degree k-1, fun fact 1 is that k points are enough to determine some missing evaluation point, f of alpha I. Probably already knew that fun fact. Fun fact 1 prime, which many of you knew, but on the poll seemed maybe some of you didn't, is that fewer than k points are actually going to tell you absolutely nothing about a missing point. So if you want to get away with less bandwidth, you're not going to do it by querying fewer points. But fun fact 2, perhaps the surprising one, is that you can do better by querying more points. So less than k points worth of information can still tell you about this missing evaluation point. So pretty cool, new things in polynomial interpolation. Okay, so that was sort of what I wanted to say about my first 2 fun facts that you thought you knew about polynomial interpolation, you thought you learned about it in high school, but in fact, there's still stuff you don't know about it. And now I'm going to tell you fun facts 3 and 4, and now we're going to move into multivariate polynomials. Cool. So in order to introduce fun facts 3 and 4, let me tell you how to use multivariate polynomials to encode data. So previously I told you how to use a univariate polynomial to encode data. But using a multivariate polynomial is called Reed-Muller encoding. This is also a very classical idea. So as before, we're going to write a file or a message or something as a polynomial. So here's my file, and I'm going to write as a polynomial, but now it's going to be a bivariate polynomial. So polynomial in x and y. And my message bits, or sort of my information, is going to be, once again, the coefficients of this polynomial. But now I have many more coefficients because I have a coefficient on x and y, but then also on xy and x squared y and so on. And let's say that this polynomial has total degree k-1. So it has an x to the k-1 term and a y to the k-1 term. And it also has an x times y to the k-2 term and so on. So for example, if f is of degree 2, then I have 6 sort of data blocks here, one for each of the 6 coefficients that show up on 1, x, y, xy, x squared, and y squared. And then I'm going to encode this just like I did before by evaluating this polynomial at a bunch of different points. So you can kind of think about this as I'm going to get a grid of points out. I pick a bunch of favorite values for x and a bunch of my favorite values for y. Okay, I'm calling these values 0, 1, 2, 3, 4. I should probably be calling them AI and AJ as before, but then the PowerPoint got too fat, so this is how it is. Okay, so you get a grid of evaluation points like this. So here's all the x's and here's all the y's. Right, so this is how you would encode data using a multivariate polynomial. And now we want to ask the same question, like what happens if one of these points suddenly becomes unavailable, right? Imagine this is shipped off to some storage node and that storage node goes down. Okay, so to try to visualize this, like here's a slightly misleading visualization. Like I have this grid of evaluation points. You can kind of view it as like if let's say it's degree 2, like a paraboloid. So this is slightly misleading because I'm drawing this as though it were a paraboloid over the reals, and like I said, we're sort of thinking of it as over a finite field. But we can think of it like this. So each one of these evaluation points lives on a grid down here, and the value is just somewhere on this paraboloid. And now one of these points has gone missing, and given the other values, I want to be able to fill it in. Okay, quiz time again. So suppose that f has total degree 2. So just something that looks like this. So here's the question. How many other points do you need to recover the missing value? So at this point, forget about the first part of the talk where I said, well, you can download less by looking at more points. Just imagine that we're just downloading whole points at a time now. And my question is, how many points do you need to recover the missing value? So go to the poll everywhere link. Same link if you just refresh the page. Now there'll be a new poll. Hopefully you can all see this here. So some people think 2, some think 4, some think 6, some think 8. No one thinks 3. Oh, there, someone thinks 3. Here, let me give you a hint. So here's on my slide. There's a hint. I just drew a parabola on the surface of my paraboloid. Whoops. Sorry, my thing crashed. There it goes. Aha, okay. Once I put the hint, a lot more people are clicking 3. Yeah. Just let this wiggle around for a little bit. Okay, cool. So let me stop sharing that one. All right. Great. So it turns out that you can do it with 3 other points. And the hint sort of shows you how. Like, if I just consider, I have 1 point on the surface of this paraboloid. If I just consider, you know, any line downstairs, like any line in my evaluation, in my original space, the space that I'm drawing the AIs from, and then I look upstairs, that slice kind of looks like a parabola. It's a univariate degree 2 polynomial. And we learned from the first part of the talk that any 3 points are enough to recover this quadratic polynomial, right? So I take my 3 points, I recover this quadratic polynomial, and now I've recovered the missing points. Cool. So this is fun fact 3, again, which perhaps you already knew, that if you have a bivariate polynomial of degree k-1, so in this picture it's a bivariate quadratic polynomial, and if you restrict it to a line, so by that I mean just like take a line in the evaluation points and then just evaluate it on that line and look at what those values are, you're going to get a univariate polynomial of degree at most k-1. So you can sort of see this symbolically by just like plugging stuff in. So suppose that this is my polynomial f of x here, or f of xy, and then I have my line downstairs I'm going to parameterize by L of z is z and then az plus b. Then I can just plug this line into the polynomial, right? And what I'm going to get is some expression with some z's in it. So all of the x's and y's are going to get replaced by some stuff with some z's in it. And at the end of the day, this is some polynomial with z, and it's going to be a quadratic polynomial because the original thing didn't have any bigger than degree 2 term, so this thing doesn't either, right? So I get some quadratic polynomial. Great. Okay. So that's the fun fact. If I have any slice here, I can recover, taking any slice of this paraboloid is going to give me a nice parabola, and hence I can recover the missing data because of the first part of the talk. Cool. All right. So again, fun fact 3, you probably already knew. But fun fact 3, again, turns out to be really, really useful in applications. And so one application that it's really useful for is something called locality. So again, imagine we're in this setting, and now this evaluation point has gone away. How do I fix it? Well, I can look at this line down here. I can think of that also as just thinking, it's like I look at these other evaluation points and pick my favorite 3, and that's going to give me the missing data. But I could also do it with another line. I could look at this line or that line or this line. Here I'm trying to illustrate the fact that, you know, it's a finite field, so things wrap around in a kind of unintuitive way. And if you look at sort of all of the lines that go through this point, so this is the evaluation point that we want down here, and I've drawn all of the lines, it basically kind of partitions up your evaluation points into a bunch of different disjoint sets because the lines only intersect in 1 point. I guess that's another fun fact. 2 lines intersect in only 1 point. And this is useful because if, let's say, you wanted to get this missing data, you could do it by taking your favorite set. Let's say you want to query the purple set, find your favorite 3 points in here to get the data. But now if someone else also wants to get that data, they could query a different set and get the data. Right? So there's sort of availability for this data here. Like I could get it in lots of different ways, which is helpful if, for example, lots of different users want to access the same thing. So this is called the disjoint repair group property. If a code has this, basically this says that every single symbol in my encoded data can be recovered in a bunch of different disjoint ways. Let's say S disjoint ways. And it has a bunch of applications. I'm going to speed through these because I see that I'm approaching my time and I want to have time for the actual new fun fact. But these are useful in applications to distributed storage and cryptography and also to complexity theory and again, cryptography. So this property shows up a lot in a variety of applications, and it's really cool that these multivariate polynomials or bivariate polynomials have this property. Okay, so now moving into fun fact 4, I want to ask you another question. Here's going to be another quiz. Let me get that one set up. All right. My question is, how about a converse of fun fact 3? So that is there some polynomial, f of xy, of degree bigger than 2, but that still has this nice property that whenever you restrict to a line, so basically any slice that you take of this polynomial thing, you're going to get a parabola. Like that is there some other funky looking thing that eludes my PowerPoint skills that is some higher degree polynomial, but so that every single slice of it that I take happens to look like a parabola? Let me know what you think. Take a look at that poll everywhere thing. Once again, it's the same website, you just refresh it. Here's the poll. Lots of people can think of one, but lots of people think it's impossible. Some people can't think of one, but by meta reasoning, like why would I be asking if the answer were no? Very good. Yeah, so look at the suspense. Let me stop sharing that. Cool, so it turns out that actually, everyone who answered was right. So sometimes the answer is no. Like over the real and complex numbers, the answer is no. There is no, you can't visualize such a thing if you're trying to visualize it over the reals because it doesn't exist. It also does not exist over prime fields, turns out. However, over f2 to the t, and in particular over f256, the particular finite field that we care about now, where all the elements are bit strings, it turns out, yes, these do exist, and there are lots of them. So this is a really cool fact. The first I learned of it was in a work by Guo Kaparti in Sudan in 2013. Madhu Sudan gave a talk earlier in this workshop. And yeah, it turns out that these things do exist, and there are tons of them. So why do they exist? So again, I'm not going to go into details in this talk, but here's just some intuition for why it works in F256, but not over the reals or over prime fields. So first, in finite fields, like stuff wraps around in a funny way. There's only like a finite amount of stuff. So that means that very high degree polynomials kind of end up being collapsing and being equivalent to low degree polynomials. So for example, in F256, x to the 256 always happens to be equal to x. So we're never going to get like super high degree polynomials. But the really nice thing about working over f2 to the t, or it works in general over fields of small characteristic, is that in these sorts of fields, remember I said that addition in F256 was like bitwise XOR? That's basically just addition mod 2. So that means that everything in sight is mod 2. So whenever you're trying to do polynomial arithmetic, a lot of cross terms just end up magically canceling. Like over f2 to the t, x plus y squared. Well, this is x squared plus 2xy plus y squared, but we're working mod 2. So this cross term just goes away, and we're left with x squared plus y squared. So that's sort of why this works, is that the high degree stuff ends up not being so high degree, and then also magically lots of cross terms just cancel. And so somehow when you restrict to lines, you end up with lower degree polynomials than you might a priori think. So this is the fun fact 4, the fun fact that you might not know, is that actually over f2 to the t, there are many polynomials f of xy like this. So there are many funky looking things, so that if I restrict to any line, all of a sudden they look really nice. They look just like a parabola. There are actually even more of these things if you only care about sort of most lines instead of all lines. This is joint work with Luna Frank Fisher and Venkat Guruswamy. There's even more of them, or sorry, there's still a lot of them when you additionally demand that all of the polynomial derivatives also agree with low degree polynomials on lines. That's joint work with Ray Lee, and there's also an additional work by Wu which does that. And in fact, there's still lots of these things, even if you look at more exotic things like lines intersected with some algebraic curve. So these things can get pretty exotic. Yeah, so these are all sorts of fun facts that you might not guess because none of them are true over the reals. But one thing you might be asking at this point is, okay, why do I care about those fun facts? That is fun, but counterintuitive, but why? And the reason in the context of storage is that you get better information density, right? So before we were talking about like encoding data like a paraboloid like this, and we had these coefficients, and the picture looked kind of like this. So this is the same picture I had before. And the property that I wanted was exactly this property, that if I take a slice, I get a low degree polynomial because then I can use part 1 of the talk, which is that univariate low degree polynomials are awesome. So instead, what we're doing is now we're saying, okay, instead of a nice paraboloid, I'm going to start with one of these funky polynomials. This has much higher degree, so it has a lot more coefficients. So that means I have a lot more data blocks that I can pack in here while still having the same length of encoding. But now it still has this nice property that every line that I look at is still a nice low degree polynomial. We can still recover information along these lines. So that's why one reason why you might care. Also, I think it's just really cool. Okay, so just to recap, fun facts 3 and 4. Fun fact 3 says that any slice of a paraboloid is a parabola. You probably already knew that one. Fun fact 3 prime, most of the time, paraboloids are the only polynomials with this property, right? So over the reals or over prime fields. But turns out over some fields, in particular, the ones that we care about, for storing data, like f2 to the t, it's not true. There are tons and tons of these. Look like that. Okay, so I'm basically out of time, so let me just do a quick summary. So fun fact 1, k points determine a degree k-1 polynomial. But fun fact 2, less than k points worth of information can give you just 1 point of our polynomial. Fun fact 3, restrictions of paraboloids of parabolas. Fun fact 4, there are things other than paraboloids that also have that property. And the moral of the story is that there are still things about polynomials that we do not know. So you might think polynomials, like high school math, you probably know everything there is to know, but it turns out we're still learning stuff. And that sometimes polynomials behave in unexpected ways, and moreover, that this can be really useful. So today I talked about sort of wave my hands at some applications in storage, but these things also can have applications in communication, crypto, computation, algorithm design, and pseudorandomness, complexity theory, and so on. And one thing I'm hoping is that maybe folks watching this talk will find even more applications. I'd love to hear about them. Okay, so that's all. I think I'll stop talking now because I'm at time, and I guess I'm happy to answer your questions in the Q&A session in a couple of hours. Thanks.
Thanks very much, Mary. Thanks for that very accessible and yet slightly terrifying talk. For those who haven't been in school for a while, it's a little unnerving, but
I'm sorry to terrify you. That was not the intent.
No, well, it's all good. It's like, yeah, so thanks for